Good morning to my friends. I'm your instructor, Mr. Koo. Welcome to Physics STPM. Today's topic is work and workout example I'm taking mainly from this book. I always look to the syllabus, tell you how much you need to know and how much is not, what is not in the syllabus. Right? You need to define using this formula. Calculate work done using force displacement graph. Calculate the work done in certain situations, including work done in a spring. So we will be going to 4.1 and we will cover a bit 4.2 and then we will prepare another video, the rest of 4.2 and 4.3. Right? So under 4.2, potential energy and kinetic energy, derive and use a formula for potential energy near the Earth's surface. Derive and use formula for kinetic energy, half mv squared. State and use the work energy theorem. Right? We will probably stop right here. Okay, let us make a start. As I said, you want to study physics, you need to have some of this book to practice. Right? This is unofficial textbook, but it's just good enough. Right? Of course, there can be mistakes there, but you're not sure, go to official textbook to check it out. Right? And some reference book, because it got model answer for you to check your answer, and you can try out. It's important to try out. Right? Not memorizing formula alone. So I'll be using mainly this book, question from this book, and past year paper. Right? Past year paper is important. This is the old one. You can get the updated one. Right? Past year paper will tell you how far the examiner required you to know. Right? This is the official textbook. Some of them you can obtain the rest from the syllabus. Okay, a bit wordy. Not enough question for you to practice. Right? But you can try them if you want to. You can try this book or that book there, or this book. This is tend to be a bit older. Definition. Right? We start with definition first. Usually, work, force, and distance move in the direction of the force. Force and distance move in the direction of the force, which we call displacement, because it is in the direction of the force. Are vector quantities. So force and displacement are vector quantity. Right? That's a distance move, and that's the force. The two must be in the same direction. So this topic has 4 sections. Work, 4.1 work, 4.2 potential energy and kinetic energy, 4.3 is power. So what is the unit? Right? Go to the formula. Force and displacement. Force is in Newton. Displacement is in meter. So instead of using Newton meter, we give it a new name, Joule, name of a scientist. That's why we capital J. This in terms of base quantity. So 1 Joule is 1 meter. A meter times 1 Newton. It's a scalar quantity. How much work depends on 2 factors. Right? Come to the formula, size of the force. How big is the force? Greater the force, greater the work. Depends on the distance moved, that X there. The further you move, the greater will be the amount of work. So 1 Joule is defined as the amount of work done when a force of 1 Newton move a distance of 1 meter in the direction of the force. Right? If it's at an angle, right? Suppose we pull with a force F, and that force make an angle of theta with the ground. That angle is theta. That's a distant move. Right? So force in direction of the right? Force resolved in direction of x, which is F cos theta. Then work done is just that force times the displacement. Right? The two must be in the same direction, so we call it displacement. So Fx cos theta. So you can either view it as right, that one there, that formula, can view it as either the force, and then you resolve that distance in the direction of the force. Right? Here's the force. Right? Resolve that one is cos x cos theta, which is the same as that one there. Or you can look at it as that is the displacement. Now resolve the force in the direction of the displacement. Right? That's your x times your F cos theta. Same. Both of them give the same answer, either one. In terms of graph, work done by a constant force. Right? That's the force axis. Right? That's the force axis. And then the x-axis is the distant move, and the force is constant, horizontal line. So you are supposed to be able to sketch the work distance graph. Right? So that area there, right? That's the distant move. That's the magnitude of the force. Right? It's Fx. Area under the graph is F times X. And then how does the work done over distance against distant move graph looks like? Same thing, right? From this formula. Work is Fx. So it's a straight line passing through the origin, directly proportional. Because it's a constant force, so it's directly proportional. Right? There's the formula. And compare the equation of a straight line. There's your y, there's your x, there's your m. So the gradient of this straight line give you the force. Right? So usually when we go to university, we define it in terms of scalar product. Force times your displacement. This is a vector quantity, this is a vector quantity. F dot ds. That is the integration. Fs cos theta, if it's a constant force. Force and displacement are vector quantities. Vector times vector, in this case, is a scalar, or it can be a vector. Okay, so your definition should be this one. Okay, so area under the graph, if it's a straight line, for the force increase like spring, force is proportional to displacement or distance move extension, then it's half kx squared. If it's not a constant force, then we integrate it, force times dx. Right? Remember the two are in the same direction. Right? Hooke's law is for your spring. Hooke's law states that the extension of a spring is directly proportional to the applied force, provided the elastic limit is not exceeded. After the elastic limit, maybe it's just a point after that. The spring does not return to its original length. That means we quite permanently deform. It doesn't obey Hooke's law anymore. So we can only operate on the straight line portion. Okay, from lower form, from STPM, right? We add the force, we find the extension. Increase the force, find the extension. That's how we draw the graph. So mathematically, we can write F equals to Kx. Compare the equation with equation of a straight line, y equals to mx. K is the gradient. Or since it's proportional, it's a ratio. Gradient and ratio is the same. K is called the spring constant, or some people will call it elastic constant, same thing. It's defined as force per unit extension. Unit, right? From this one, K is F divided by X. Force is Newton, M is meter, so it's Newton meter minus 1. So you might want to show that it's equal to this one in terms of base unit. So in experiment, we find the gradient. But when it comes to exam, the fastest way is to take the ratio. Let's take the extension, and take the F1. And K is from F1 divided by X1. Right? K is a measure of the stiffness of a spring. Let's look at energy. What is strain energy or elastic potential energy? Ability to do work as a result of a change of shape of an object. Right? Change of shape is the stretching. You stretch the object or you compress the object. Right? So let's look at the force extension graph for spring. Energy stored in spring. Potential energy stored in spring. Work done in stretching the spring. Force times distance moved in the direction of the force. Right? Remember, this one should be calculus form. So it's shaded area. Or another way is to look at an average force. Average force is a constant force that act over the same extension, that gives the same energy or work done. Right? So it's W equals to half Fx. Memorize. As F equals to Kx, replace the F here with this Kx. We got half Kx squared. Energy stored in spring, right? Different name. Potential energy stored in spring can be called strain energy stored, elastic potential energy. So it's the area of the triangle. Work done in stretching spring, same. We can either use average force times extension. Right? That's the symbol for average force times the extension, x, right? Which is the area of rectangle, must be equal to the area of this triangle. So that's the area of the rectangle or average force, and that is the average force over the same extension. So this area of triangle, and then we compare. Right? These two are the same. So half x equals to average force. Energy transformation. Work done on the ball. There's the ball. There's a string. So work done is stored in the ball and the string as elastic potential energy. After release, the arrow is said to have kinetic energy. So energy is measured in joule as work. The conservation of energy in this case, loss in potential energy in this case is elastic potential energy. Then as the arrow shoot off, we gain kinetic energy. Or in terms of maths, we can write this formula. Okay, remember the definition. If it's not a constant force, then we have to use integration. Solving problem. This is from 2014, November, paper 11. Each year, there are each year or each semester, 6 months, we have 3 papers for the exam for different regions of the world. This is Cambridge A-level. A rubber band is stretched by hanging weights on it, and the force graph is plotted for the result. The best estimate of the strain energy stored in the rubber band when it's extended 30 cm. You're asked to estimate. Right? So you can draw triangle and rectangle. Remember the area is on this side, the extension side, not on the force side, but on this side. So you can use rectangle, break it into rectangle and triangle. Right? It's just an estimate. Strain energy per unit equals to area in the graph. Objective, you don't have to be so particular. You just estimate and then they are quite far away. Right? So area of this triangle, which is this one. Area of this triangle, which is that one there. And then area of this rectangle, which is that one there. And remember this is cm, so we have to convert it to meter. Use your calculator. Right? So the best answer is close to this one. We overestimate. November 94, this is an old question, A level Cambridge. 94, paper 1, question 23. A spring obeying Hooke's law has an unstretched length of 50 millimeter and a spring constant 400 Newton meter minus 1. What's the tension in the spring when its overall length is 70 millimeter? Okay, that's the formula. Force is force constant or spring constant times your extension. The spring constant is 400. Original length, extension, this overall length. So you subtract to get the extension. And millimeter, you have to convert it to meter. So it's 8 Newton. The answer is A. Okay, have a go at this one. You may want to stop the video or to try this one. This is a subjective question, Cambridge A level. A weight W, that's the weight, hangs on a trolley that runs on a rail. That's your rail. That's your trolley. The trolley moves horizontally through a distant P. Trolley moves that distance and simultaneously raise the weight to a high Q. So then the weight is raised to a high Q. As a result, the weight moved through a distance R. That's a distance move. If you want to shortcut from X to Y, it starts from rest. It starts and finishes at rest. Right? Stationary. Start stationary. Stop also stationary. How much work is done on the weight during this process? Okay, that's the weight. That's the weight. Right? So the weight and the displacement might be in the same direction. That's the key definition of work done. So gravitational potential G equals to mgh or your x in this case. X is your q to wq. Okay, distance in the direction of the force. Not that distant. That one is perpendicular to the force, so not work done. Okay, let's try your partial paper STPM. A body moves in a straight line from rest on a smooth horizontal surface when a constant force acts on it. Which graph shows the variation of work done? W with time t for the motion. Right? Constant force means constant acceleration. So U is 0. So our form of definition, work done is F times S. S is the displacement, but we want time. So we have to replace this S with our time. So we consider motion. Right? S equals to ut plus half at square. U is 0. So it's half at square. So replace that S with half at square. We got our F, half at square. So these two are constant. All these are constant. So it's in the shape of a parabola. Right? This one is polyhedron. It should go slightly there. Okay, let's go to potential energy and kinetic energy. Right? Suppose to derive it and use the formula, same with kinetic energy, and then state and use work energy theorem. So we stop somewhere there. Then continue this one on another video. Right? First, energy is the ability to do work. The wind turbine generator has energy, so we let it do work. A moving body has energy because it can do work. To calculate the energy in a body, we let the body does work. So energy equals to work done. So kinetic energy, you can use KE or can use K. Kinetic energy is energy of motion. Because anything that's moving has kinetic energy. Energy of an object, kinetic energy of an object is the energy it possesses because of its motion. Right? You can use EK or can use KE or can use K. M is the mass of the object. V is the speed or the velocity, doesn't matter. Right? In this case, it's square, it becomes a scalar. Derivation of this formula, half mv squared. So we start with the object or mass m at rest. We apply a force there. Let the force move a distance x, and then it gain a velocity v. Force is still acting. So kinetic energy equals to work done. That's your work energy theorem. Then we consider linear motion. Right? Initially, u is 0. Then final is v. Distance s move is your x. Acceleration is your a. Acceleration due to this force. So v squared equals u squared plus 2as. Okay. So our u is 0. Our s, we replace it with x. So we get 2ax. Or ax is half v squared. Right? That's what we derived just now. So we use kinetic energy equals to work done. Force times distance. Force times distance. Force F, distance x. Then we can replace it from here if you want to straight away. Right? Replace your F with MA. X. Right? Replacing this AX. Right? With half mv squared. That's how we derive our kinetic energy formula. You need to know how to derive it. Right? Have a go. Close your book and then do on a piece of paper how to derive. So we work energy theorem. Right? Gain in kinetic energy equals to work done. So in this case, we don't need to derive. Right? We should be able to write down. This is initial kinetic energy. This is final kinetic energy. The force is the one, the work done is the one that causes a gain in kinetic energy. So you should be able to write. There's the final kinetic energy. There's the initial kinetic energy. There's the work done. Right? No friction is involved here. It's just the work done, the force cause a increase in kinetic energy. Potential energy, U, PE or EP, is the stored energy available to do work. Remember, this is a general definition, right? Because there are three types. Chemical, right? It's stored energy, but it can do work. Elastic energy, spring, store energy, or gravitational potential energy. Right? We have done for spring earlier. Gravitational potential energy, EP or PE. Right? Remember, the key is near the Earth's surface. Near the Earth's surface is about 1,000 meters there. Right? 1,000 meters above the surface there, up to there. We will see this later on when you study, I think, topic 6 under gravitation, where G will change after that. Value of acceleration due to gravity varies with distance. Gravitational potential energy of an object of mass m at a high h is given by, as the object of mass m, that's your high h, mgh. Depends on mass, greater potential energy, greater height of the object, greater potential energy, and depend on g, gravitational field strength or acceleration due to gravity. Remember, in this case, the force is attractive. The Earth is pulling it down. Right? Derivation, we consider that object of mass m, we lift it to a high, we want to do work, so we lift it up to a height h. So gravitational potential energy is equal to work done. Right? Force times height. Right? Force times height move. Force is your weight, mg, is mgh. Right? So we are do work energy theorem, work done equals to gain in potential energy, or Fh equals to mgh. An object at high potential will move to one of low potential, right? Because the force is attractive. You want to go to a zero potential energy level. So in this case, we always will treat the surface of the Earth as zero potential energy. Right? Gravitational potential energy and elastic potential energy. What's the difference? Gravitational potential energy store energy due to its position or height above the surface of the Earth. Elastic potential energy store energy due to material being stretched. Is either the material is stretched or compressed. So it's stored as elastic potential energy. In these cases, ball dropping for a high h or rolling down a slope, right, a smooth slope of high h, or moving down steps, ball moving down in steps, high h is the same. So the work done or potential energy is the same, mgh. Okay, this is more for later on, I think topic 8 under thermodynamic. But it's okay, we can study a bit extra earlier. Work done by gas, right? Since we are under work done. Work done by gas, expanding at constant pressure. Here we look at constant pressure, P is constant. Right? There's a initial is equals to P times delta V. That's the initial position of the piston, frictionless. It moves to a high H, or that is the final position. The pressure is still the same. Right? So that one is an increase in volume or change in volume. That's a constant pressure. Pressure of gas. Work done on gas. Right? Work done on gas is compression. We are adding energy. The work done becomes energy given to the gas. Work done by gas, expansion. So when it expands, that's work done by the gas. It must come from something. It must come from somewhere. Right? So it must come from the gas itself. Right? Derivation. Right? There's a pressure, gas pressure, there's external pressure, they are the same. Right? It doesn't change. The piston move a height or distance delta D. So we use the work done formula for force times distance, that's your work done. So replacing the force, right? Force, we define later on force divided by cross-sectional area, take the A across. So F equals to PA times your distance move is delta D. So A delta D is your change in volume. Okay, so P delta V. And if you look at the what does the shaded area, right? It starts with V1, it moves to V2. Can show on the graph, constant pressure. What does the shaded area represent? Work done. Right? V times delta V or V2 minus V1. Arrow, this arrow show is expanding. or if it's a non-uniform pressure, then we use calculus. Integrate from V1 to V2. Energy transformation, in this case, no friction. Right? The force increase the velocity of the car from U to V after a distance move with X. So you should be able to write the equation. Right? Work energy theorem. Same. Initially, it is velocity U, no air resistance. Right? The ball is thrown up, it moves to a height H, has a velocity V. So you should be able to write the work energy equation. Right? This is high kinetic energy. This is low. Right? So there's a loss in kinetic energy from here to here, but there's a gain in potential energy. Low potential energy here, high potential energy. So in this case, it's kinetic changing to potential. Right? So there's a loss in kinetic energy. There's a gain in potential energy. You should be able to write in equation form. That's larger, half mu squared minus half mv squared, lower kinetic energy, equals to your mgh. That's the height, not from the ground, but from where you start. Conservation of energy. Right? Object moving up a slope. That's the applied force. Right? The thrust if it's a car, and that's the distance move up the slope. Displacement. So if that block of wood or object move at constant speed, right? That's the weight mg. There's your friction. It's a rough surface. There's a height in move. So you should be able to write down your work energy equation. Work done by force. That's the force. It does the work. Take it to the height h. Work done against friction. There's friction there. It's a rough surface. So the work done will go to, work done by this force will go to work done against friction. Right? Constant speed, so no kinetic energy change, but there's a gain in potential energy. So energy input, F times X, that's your work done. Energy output is mgh, right? Because there's a gain in potential energy, that's a useful work wasted. Right? This one doesn't benefit us. It's finally lost as heat or thermal energy. So efficiency in this case is just your energy output over energy input. Energy output is mgh, energy input is fx. Right? Should be able to write this equation. Right? In collision, we hear sound and the cars are smashed up. So in this case, energy transformation, kinetic energy of the moving car is transformed into sound and work done in deforming the cars. Right? Car all bent up, damaged. So that is where the work done goes through. Because you touch the car, you feel it warm. So that is internal energy. So when it's warm, it loses thermal energy to the air. Right? Internal energy causes a rise in temperature of the cars and tires. And finally, loss as thermal energy to the surrounding air, increasing the internal energy of the air. That means the air moves faster because there's an increase in kinetic energy. How does the kinetic energy displacement graph look like for no air resistance? Right? Initially, the object is at high potential energy. As the potential energy decreases with height, kinetic energy increases. Yeah, dropping an object initially has high potential energy. then the kinetic energy increases. The height becomes smaller, so the potential energy becomes smaller. So total energy is constant, right? No air resistance. So total energy at any time is just the kinetic plus potential. This is called conservation of mechanical energy. So you should be able to draw your graph. Right? Height above the ground that drop the object. So is it basically that equation to is a straight line. Right? It starts with high potential energy. You drop it from here, it's a straight line going down to ground. Then the total energy, right? Potential energy, the kinetic energy is just your total energy minus your potential energy. So kinetic energy, initially when you drop it to 0, then increase to maximum. And the total energy is constant, doesn't change, no air resistance. It's just potential change to kinetic. Okay, if you look at the mass involved, right, initially you drop it, speed is 0, so total energy is mgh, h is the height of the ball. But we are not interested in a constant height. We are interested in the height that is changing at any time. It will be at a high h, but we are measuring your y from here, right, from where you drop the ball. So we replace that h there with our h minus h minus y. Right? We want this height as a potential energy. So it's just your that capital H initial position minus your distance drop y. Right? Replace that h with h minus y. So that's the reason why we get a graph with a negative slope. That one there, right? MGH there. Right? Compare the equation of straight line. That's why we see the graph. Then our total energy is EP minus EK. So it's E minus your EP. Right? So that's why we get MGY. So that's why we get a straight line passing through the origin. Okay, just to review the same thing. Okay, let's try the question from the reference book. Quick check. Page 95, example 4.1. An object of mass m passes a point P with velocity u and slide up a frictionless incline to stop at Q, which is at a height h above P. A second object of mass 2m, now we change this mass to 2m, passes P with, instead of u, it's now 2u. What's the height? Right, so it's a conservation of energy. Kinetic change to potential. So this, as it moved from P to Q, it lost kinetic energy. It gained potential energy. So it's half mu squared, right? Initial mgh, h is the height. Then m and n cancel off. Right? Take all the constant to, right? G is a constant. We take a constant to one side, and u squared take the h down because u squared h equals a constant. Then let the two be variable. This is the final one. This is the initial one. It must still be constant. So you want h2. This one across there. Okay? Place in your value. This is the initial one. H, u2. u2 is 2u. u1 is u. Right? 14 square. U and u cancel off. So it's 4h. So answer is donkey. Okay? This one is from example 1.1 from your earlier lecture. And you need to remember, right, how to resolve the weight into component. That's the perpendicular to the surface. This one, the angle is theta. This angle is also theta. So this perpendicular component is parallel to the plane. Right? Parallel to the plane is W sine theta. Remember that? Memorize that? W sine theta. Perpendicular plane W cos theta. Okay, so let's try this equation. A block is, for example, 4.2. Quick check. Quick check 2, page 96. A block of mass M, the one there, at P slides from rest down a plane inclined at an angle theta there. The friction on the block is F. That's your friction. After sliding through a distance D, the velocity of the block is given by, you want the answer. So write down the work energy theorem. Right? Draw the diagram. Right? Resolve the weight component because it's moving down the slope. Mg sine theta. And there is your friction F. Right? So basically, you got kinetic energy. Right? Sorry, it has at rest no kinetic energy. When you move down a height h, you gain kinetic energy, you lost potential energy. Right? Or summarized in this triangle, there's the height, there's the distance move, there's the angle theta, and the relationship you must know, sine theta is h over d. So our final kinetic energy initially is 0. Potential energy initially is mgh, finally is 0. Work done is just your work done against friction, F minus, because it's, the force is opposite to the direction of motion, right? Or it's work done, that's loss, F minus D. Right? Basically, the potential energy is converted to work done, and that's why work done should be here. I take it to across there. Right? The initial potential energy goes to work done against friction and also cause a gain in kinetic energy. Okay, it's just simplify the step. So your H, replace the H with D sine theta, FD. So your answer is B. Okay, so we have completed this for today. We will complete 4.2 conservation energy, work out example, and then we complete power. Okay, so thank you for this morning. We will stop here. Okay, see you next week. See you the next lesson. Bye bye.